Well, welcome everybody. We're from the team Spirit of Amsterdam. First we're going to do an introduction. I'm Ingmar Hendricks. And we're from the Hogeschool van Amsterdam, in Amsterdam, of course. We're the winners of last year, the 2009 race. And well, maybe some of you recognize Guus and the others of our team. Most of our team are still the same members. Some members have left, and we also have additions to the team, which I'm one of. Let's go further. First, we're going to do a little overview of the Spirit of Amsterdam 1. It's the white car over there. It's the car that we won the race with last year. And then we're going to talk about our new car, Spirit of Amsterdam 2.
So this is our car we won with last year. It's well, I'm gonna go very globally over. We had a measurement speed of 52% here. We had a little bit more in test, but it's not official and no official measurement, so we can't brag about it. It was we had a standard rotor of the company Donkey. We bought it off them, I think. We use a standard rotor and a standard engine block for gearing, which seems a very popular idea here. And well, we had a whole year of, a half year of building and testing it. So we had some experience with it and some good ideas to build the next one. We came to the conclusion that it was very handy to have a car which you can adjust easily. You need to adjust your gearings often. We think we won the race because we adjusted our blades. We had a 3-blade propeller, but we needed more torque, so we mounted a 5-blade propeller. But on other things we experienced was that it was very heavy. That's unhandy if you want to transport it, but also for a moving vehicle, weight is never a good thing to have. So also the gearbox steps we thought were very big, because on a wind turbine you have a very big power peak in your power to RPM ratio. And we had the feeling we were never really on the power peak, so we figured we needed smaller steps in our gearings. For that you actually need a CVT, but CVTs don't run as smoothly as we think we do. Don't run as smoothly as we want them to. So we built a new drive, which I will explain next. We did believe in the turbine. The turbine was well, we had good experience with it. The other thing we thought is that it was really built too heavy. It was idiot-proof. Some of you might have seen we're sitting with 3 guys on the back and 1 girl in the front this afternoon, and it was still driving. So that might be a bit of oversized plane.
This is the new car. This picture was taken last Friday when we had our test drive. First of all, we're going to talk about the additions of the concept, so what we added this year to our new vehicle. Maybe Chris can tell us something about it?
We have a dual transmission, which means we have 2 chain drives in it. For those transmissions we have the 2 roll-off gear hubs, which are used on bikes. We made them, we chose the chain drive so that we would have half steps on it. A normal roll-off hub has steps of 15%, so we have 7.5% gear steps, which is a lot less than we had last year. Therefore, we hope that we can have a more efficient, we can hit the power peak better.
Second of all, we have an electronic control system with the car. Because we have a dual transmission and every roll-off has 14 gears, so in total we have 28 gears on both transmission lines. For that we need an electronic control system to do the gears shifting automatically, because it reduces the human factor and the error, the mistakes you can make while driving. No offense to our driver. So that's why we created an electronic control system to maximize the performance, of course. The control system is actually capable of measuring all the sensor data and then having special actions take place.
We also have reduced weight a lot. The first thing we reduced weight on was the turbine, which is a standard turbine as it's standing there. There's a big metal frame in it, a thick plastic body. We had it out of foam now, foam and glass fiber. So it's a lot lighter. And we also have a more aerodynamic shape. It's not really true, the shape is pretty much as aerodynamic as it is, but we had a much smaller vehicle, which means you have a smaller frontal area and therefore less drag.
Now we're going to talk about the construction process, how the construction process of the last 6 months what we did and how we did it. First of all, the wind turbine. Well, I first told a little bit about it yet.
Yeah. We wanted to make our own wind turbine because, well, the ring actually turbine is. So we had the profile of last year, and first we wanted to make it ourselves. We tried to have a big milling machine and shape it by hand. This turned out to be a big hope of styrofoam, and nothing came out of it really, I have to admit. So we had it milled at a company for us. It cost a lot of money, but the results were very nice. And this milled foam we laminated with, hand laminated with glass fiber, in some places carbon fiber, where we need it. And that way we came out on a pretty nice turbine. It weighs about 40 kilos, we think. We also have a frame in the body. We reinforce the body because that way you get somewhat of a half monocoque construction. With this frame in the body, we have the whole chain right on it. It's a nice story to tell that the whole frame is welded by students, so don't blame us for nasty welding. You can see here that we have 2 chain types. Actually, the chains are all here. These are electrical clutches. These clutches are controlled by Ingvar also.
Control system that we're going to talk about.
And the frame is bolted into the body, into the reinforced body. So that way we can take out the frame pretty quickly and make any adjustments we want on the frame. That way we have an even more flexible car than last year.
Well, the gear transmission. First of all, like I already told, we need to do automatic gear shifting. You can see right here the control system, the electronics panel, and of course the dual transmission line below. Then we're going to talk about the electronics. The electronics are capable to shift gears. It has a clutch that allows us to shift gears on one transmission line and then switch the power or the motion from one line to the line that we just shifted. So that way we can shift our gears without much
breaking the hours.
Yeah, without breaking the hours. But of course, it's a student project. Things can fail. Algorithms may be proven faulty. Something may go wrong. It may rain on the electronics, which is also very bad. So that's why we have, So that's why we have a backup manual control system. It basically allows us to shift gears with buttons, and then it also does it automatically, but it doesn't automatically shift. You have to still push buttons and decide when you want to shift. First of all, we achieved this by having several sensors in our car, and of course around our car, actually on top. It's a little thing coming out the front. That's our wind sensor, and we also have RPM sensors. Furthermore, we also log our data on a SD card, which allows us to analyze all the performance of a particular run, so we can see whether the programming or whether the control system has functioned correctly. We can tweak the system, and of course we can calculate how efficient we were during several parts of the run itself, so not only the entire run. The electronics, it's basically very simple. It's a very modular design. We have several sensors. Those sensors sample data. That data is then transmitted to a sort of central hub where all the data is stored on a microprocessor. And from that hub, several modules can request data, which is like the ST data logger and the control system. They request the data. So it's a very modular design. You can just, if you have a new module, you can just plug it in, and then it should work. Should. So, well, that's the basic idea. Of course, it's a little bit more complicated than that. We have 10 microprocessors in the electronics, which all of them have specific tasks. And of course, we have several redundant systems, which we hope we don't have to use. So, well, that's the electronics. Of course, me being a programmer, I have to end with this. So, if there are any questions, yes. Yes.
Okay, I think one last question, and then.
Over which time do you average your sensor data for the control system?
When how much time we average the sensor data?
Yeah.
Well, the wind sensor itself has a filtering system built in. So the pole actually in front of the car, it can wiggle a little bit. That filtering system can filter that out, and then it produces wind speed. I think every 0.5 seconds. And then the RPM sensors do it even faster. They do it, I think, every 4 times per revelation, per RPM, per round.
Thanks.
Yes, well, thank you for organizing this event.
Yeah, thank you for having me.
Thank you for having us again.